In the previous video, we looked at the concept of latent heat during phase change. So let us move a little further and look at what it might look like when you graph this information. So I have a roughly made table. Let's say you conducted an experiment in which you took ice at minus 10 degrees Celsius and you started heating the ice, and while heating it you measured the temperature, noted down the details across a long period of time until it melted, turned from ice into water, and then uh, came to its boiling point and then started getting converted into steam. So the phase change in this situation is taking place over here. So here the ice turns to water, and over here when the water turns to steam. So these are the places where there is a phase change. Okay, and what we have seen is that it is during this phase change that the latent heat is being absorbed. So these are the two phases latent heat is being absorbed. Now we come to the next important concept in this, which is called as the heating curve or the cooling curve. Remember, you can also perform this experiment backwards. If you take steam, which is at temperature above the boiling point of water, and then you reduce the temperature, you will notice exactly the same thing. But for water, this is an easier way to perform the experiment. Um, Now what you do is, if you graph the two values, time against temperature, okay, so you put the time in the x-axis, increasing in that direction, and the temperature in degrees Celsius on the y-axis. Okay, and this is increasing in this direction. So then what kind of graph will you obtain? So let us say that the temperature starts with minus 10 degrees Celsius and goes all the way up to, let's say, 98 degrees Celsius. Okay, and the reason why I'm taking 98 degrees Celsius or maybe 99 degrees Celsius is because in general the water that we use, unless it is distilled water, pure water without any impurities in it, the temperature of the boiling point will be slightly less than the 100 degrees Celsius which we are used to. So 100 degrees Celsius is the temperature at which pure water boils. Okay, so therefore similarly the temperature for melting of melting of ice into water would also be slightly above that value of 0 degrees Celsius, but in this case I already put it as 0 degrees Celsius, so we'll leave it at that. So as the time increases in minutes, 1 to, I don't know what, maybe it will take 20 minutes to do this. Okay, then you will find that the temperature plots will go up in this manner. Okay, so the temperature is increasing until it reaches the value of 0 degrees Celsius. Now at the value of 0 degrees Celsius, for a few minutes, maybe 2, 3, 4 minutes, the value will kind of plateau out. Okay, until all of the what ice has melted into water. Then since you are continuing to heat it up, the temperature will rise further until it gets to around 98 degrees Celsius, and then there will be few values in which again it will plateau out. And then if you are able to, and generally we are not able to do this, that is when it gets converted into steam, then the temperature should rise again. So the critical phase in this are these two regions, this region over here and this region over here. And these are the places where your phase change takes place. So this period of time during which the latent heat is being absorbed to increase the intermolecular distances so that ice melts completely into water is one phase change. And this phase, again, when it happens, the water absorbs the energy, increases intermolecular spaces and gets completely converted into steam. Then the temperature of the steam, if further heat is provided, will rise. So interpretation of this graph, which is sometimes called the cooling curve, which is a misnomer for this particular graph, because this is the heating curve. Because you can reverse the entire process, then you will get a graph that looks like this. It will be the exact mirror image of this. Then some interpretation is required in our syllabus. So what they do generally is they give you a cooling curve and they ask you to say at which point is the phase change taking place. So typically they will say that there is a point A and there is a point B, and then there is a point C and there is a point D. Okay, so A, B and C, D. So they ask you to say that identify the time period between which phase changes are taking place. So you answer A, B is one period of time in which the phase change is taking place, and C, D is another phase of period of time in which the phase change is again taking place. Then they might ask you what is happening during this phase change. Then you have to explain that during the phase change, latent heat is being absorbed to increase intermolecular distance and convert all of the ice into water or all of the water into steam. Now, the amount of heat energy that is being absorbed in this phase is called as the latent heat of fusion. Okay, latent heat of fusion or latent heat of melting, they use two different terms. So you say latent heat of fusion, and over here you would call it latent heat of vaporization. Hope that comes in the video. Latent heat of fusion and latent heat of vaporization. Now the next question that can be asked is, this latent heat of fusion and latent heat of vaporization, is it a fixed number? Is it something that is characteristic of the substance that you use? Yes, it is. So if you take ice and if you take water, the latent heat of fusion and the latent heat of vaporization are fixed quantities. So what are those fixed quantities? And of course you can perform experiments to get an approximate value of this. But for the sake of doing calculations, we have come up with certain figures according to careful experiments that have been conducted using pure substances. So the latent heat of fusion for ice to water is approximately 336 joules per gram, which means that every gram of ice at 0 degrees Celsius will absorb 336 joules of energy to get converted completely into water. Okay, so this is a number that you have to remember. This is a number that you'll have to memorize, although in most numerical questions involving latent heat, you will be given these values also for calculation purposes. Similarly, there is also a latent heat of vaporization for water, which is approximately 2260 joules per gram. So there is a huge difference in the values of latent heat of fusion and latent heat of vaporization for essentially the same substance. And this you can also compare it with the specific heat capacity of water, which is 4.2 joules per gram. Okay, so these three values are something that are worth remembering per gram degree Celsius, I should write, because this is a amount of energy required to raise 1 gram of water by 1 degree Celsius. Okay, so that is between these two phases. Okay, but 336 joules per gram, almost 100 times of this number is what is required to convert it from ice to water. And here note that degree Celsius is not mentioned because there is no change in temperature. Similarly, approximately 4 times this value is required to raise the temperature of Water at boiling point 98 degrees Celsius or 100 degrees Celsius, in this case it will be 100 degrees Celsius because we are talking about pure water, to get converted into 1 gram of steam. Okay, so now with these values you will be able to perform calculations that are necessary for numerical problem solving using the same concept. So just to go over it quickly, if you do a cooling curve or a heating curve graph, temperature against time, as the time increases when you are providing energy, the temperature will rise up to a point which is the melting point of ice, where there will be a plateau, so there will be a flat part, and then there will be an increase again of the temperature, and then there will be again another flat part where the latent heat of vaporization takes place, and some interpretation of this graph will be required. Typically they will give this as a line which is connected like this, and then you will be asked to do some interpretation work based on this, and I hope you will be able to do the required interpretations accurately.